Good morning, everyone. Well, that's very loud. I might have to be a little bit louder in the microphone today. They're doing some work out in the hallway, obviously. So we're going to continue in our review packet. I just put up the equations and supplied information for midterm 3. A few things to be aware of is you get the Rydberg constant, you get the speed of light, you get Planck's constant, you get these equations down below, C is equal to lambda nu, E is equal to h nu. This equation here, I kind of give a little caution to because you have to make sure to use that when you're dealing with the wavelength of matter, not for the wavelength of light. So this is for matter. This is the de Broglie wavelength equation. That's probably an equation you're not necessarily going to be looking to using unless you're asked for the wavelength of a particle where the particle has a mass. If you're asked about the wavelength of light relative to the H atom or just for any wavelength to frequency type problems, we're using these conversions in these equations here. These two equations here, we're going to see for the first problem that we're going to work on, you could use both of those equations to solve for the transition of an electron within an H atom. So these are used for the H atom emission spectrum type problems, wavelengths associated with those transitions, or for absorbance, what wavelength could be absorbed by the H atom as it increases in energy. And then this second equation here, or the final equation here, is also for matter. This is the uncertainty principle. So the last two equations are the ones that are getting toward light behaves as a wave and light behaves as a wave where we don't know where it is. Sort of equations that kind of led us to maybe some more broad conclusions that led us into orbitals than necessarily into math problems. But we do get these equations down here in case we need them. Okay, so the first question for today is the one we left off with last time, which was, calculating the wavelength of light that's emitted for an electron in an H atom that goes from a high n value of 4 to a lower n value of 3. And so this should lead to emission because we have a higher energy state, the n equals 4, transitioning to the n equals 3 state. So we should have light given off here, emitted by this process. One of the things I was mentioning at the end of class last time was that we might recall that the 4 to 2 transitions were in the visible. The 4 to 2 is a visible transition. The 4 all the way down to the 1, the n equals 1 to 2 is a big difference of energy. So n equals 4 all the way down to the 1 is a UV photon. So we might be expecting this to be in the infrared region. So if we had 4 choices and we're pressed for time, we're at least probably picking a transition that's not in that 700 nanometer or lower range for this transition. Now, we could calculate this one of two ways. We can use this equation here with the Rydberg constant. And that works just fine. In fact, this is probably the faster way to solve the problem, the way I often solve the problem. The reason why I don't necessarily run to this equation is I just prefer to see, and I just like to make sure I understand that the atom is losing energy from the 4 state into the 3. So I calculate the delta E for the H atom, just so I can see the loss of energy as I go from my final state, E3, minus my initial state, E4. So I'm just taking my final minus my initial. So E3, the energy, the n equals 3 states. My final state, my n equals 4 state was the initial state. And so then I can just plug this into here for minus 2.18 times 10 to the minus 18 joules, because that's my equation here for energy as a function of n is just negative 2.18 times 10 to the minus 18 joules times 1 over the n value squared. And then minus, so keeping the minus sign here, and then e to the n is still minus 2.18 times 10 to the minus 18 joules times 1 over 4 squared. And so I can calculate the change of energy for the H atom as it goes from its, between its final state of the n equals 3 compared to the n equals 4, the initial state. So, and this also just makes me use a calculator, right? So I go negative 2.18 times 10 to the minus 18. So negative 2.18 e minus 18 divide by 3 squared. So divide by 9. And then I go minus negative 2.18 e minus 18 divide by 16. Because 4 squared, of course, is 16. And so this gives me a negative energy, meaning the atom's losing energy. I like to see this, and I like for us just to be able to understand that the atom is losing energy. Atom should lose energy. It went from a higher state to a lower state. So the atom lost energy. Where does the energy go? the photon absorbs or obtains the energy lost by the atom. It's kind of like a system versus surrounding problems. I like to think of it that way, that the atom lost energy. Where did it go? It went into the creation of the photon.
Are we going to get that wave on the reference sheet? Or?
This one here?
Yeah.
Yeah, I think it was on the slide I just mentioned before. It's on the supplied info sheet. And this one is too. And I think if we understand this, we can probably just plug in here, look up the Rydberg constant, and solve as well. That'll get us the wavelength just as fine. But here, we also get it just with another approach, another equation. And so this is the energy of the photon. Energy of a photon is equal to hc over lambda. So we're just solving wavelength for wavelength from taking lambda as hc divided by 1.06 times 10 to the minus 19 joules. So hopefully we're all comfortable with H, or if you're not, just look it up. But it's 6.626 times 10 to the minus 34, and that's joules times seconds. We multiply that by 2.998 e to the 8, and that's meters per second. Just kind of writing the units in, and then dividing by joules. So I divide by that answer, and I get 1875. So I get 1.875. So 1.875 times 10 to the minus 1, 2, 3, 4, 5, 6 meters. And wavelength's almost always going to be asked for in nanometers. I don't know if it's specified in this problem, but almost always on a test, you're going to want to put this value into nanometers. So 1 meter, it contains 10 to the 9 nanometers, so multiply that by 10 to the 9. Gives me 1875. So I guess that would round to 1870 nanometers. It was like 1874 point something, whatever. Okay, so 1870 nanometers. And this, if we're asked for what region of the electromagnetic spectrum this is in, just remember 400 to 750, this is our visible. And so if we're on the plus side of this, that's the infrared region. Now you might say, how do you know it's not microwave? Well, we probably wouldn't give that to you as a choice, but it's within an order of magnitude or so of the visible. So more than likely, that's going to be the infrared region. The regions of the electromagnetic spectrum are pretty broad in terms of their wavelength range. The visible, the ones that's really small. The visible is a really small, narrow range, is 400 to 750. The UV is less than this on the other side, so this is down to about a handful of nanometers and up. Less than that gets into the X-ray, gamma ray region. So that's how we can calculate a wavelength for an H-atom transition. So the conclusions derived from which theories applied to an electron supports the use of probability distributions, or which theories led to probability distributions or orbitals for how we discuss where electrons are in multi-electron atoms. So these were coming from those experiments that we're mentioning on that equation sheet, the de Broglie wavelength and Heisenberg's uncertainty principle. So those are the main theories that we were using. The results of those theories showed us for the relatively light and fast electron that particle behaves as a wave in a way that more classical objects like a baseball or other objects don't behave or have a wave-like motion that's important for their motion. But the electron being so small, so fast-moving, that it behaves as a wave. That's from the de Broglie wavelength. And then also as a wave that has an inherent uncertainty where we don't know where that particle is at any given moment. All particles actually are subject to the uncertainty principle, but it's just that their speeds and their size don't make the uncertainty principle lead us to having such an issue of identifying the momentum or the velocity and the position of the particle at the same time. But for the quantum mechanically behaving electron, we have those issues. So these two theories here led us to the orbital picture of matter. The second two choices, Pauli exclusion and Hund's rule, these are about how electrons fill into their different configurations. So those are about electron configuration, filling orders. The Bohr model and the Balmer series, those are just about the H-atom transition. So the Bohr model is just a model that gives us an accurate picture of the energy levels of the H atom, but doesn't really discuss where the electrons actually are. It doesn't really give us a good picture of how the electrons are behaving. We need to look to more advanced quantum mechanics, like trying to use the Schrodinger equation, looking at actual orbitals, looking at probability diagrams. Those are giving us a better description of how electrons are behaving in multi-electron atoms. Then getting into quantum numbers, n's the size, l's the shape, m sub l is the projection. The number of the m sub l's are the number of different orbitals that are possible for a given subshell. All the orbitals that share an n refer to the shell. All the orbitals that share an n and an l refer to a subshell. So this is referring to a subshell, or the n equals 3 is telling us that we could have one of 3 possible L values. L could be 0, it could be 1, or it could be 2. And so we'd have the 3s subshell, the 3p subshell, and the 3d subshell for these different L values. But when we see that m sub L for a given orbital is -2, that kind of rules out for this orbital that this orbital has to be specifically a 3d. Why is that? Well, the range of m sub L is -L through 0 to plus L. And so if we have an m sub L of -2, then the only possible L value for that orbital would be 2 for the L. So L has to be 2 for that orbital. If L is 0 or 1, if L is 0, the only m sub L possible for the orbital would be 0. So we couldn't have an m sub L -2 if the L is 0. If we had an L of 1, the only m sub L values could be -1, 0, or 1, not -2. So this question here is just getting at the kind of range of values. So our m sub L is limited to -L and plus L. So the only possible m sub L here would be 2. Now the max L can be is n-1. So once you get to n-1, n is 3, so the max L can be for that shell is 2. So if we wanted to get up to an L of 3, that would be for an F subshell, we have to have an n of at least 4. So at n equals 4, then we can have an L of 0, 1, 2, or 3, meaning we can have a 4s, a 4p, a 4d, or a 4f subshell. And then the 4f subshell would range, the m sub L's would range from -3, -2, -1, 0, +1, +2, +3. And so that corresponds to 1, 2, 3, 4, 5, 6, 7 4f orbitals. So the 4f subshell would be comprised of 7 orbitals. The 4d subshell, just like any d subshell, would be comprised of 5 orbitals. The 4p subshell, just like any other p subshell, could be comprised of 3 orbitals, and all s subshells just 1 orbital. And then we can get 2 orbitals into each. Each orbital can have a spin up or down electron. Okay. So doing a couple configurations, so let's look at tungsten. Sometimes we're told like this here, just so we can help find the element on the periodic table. Element 74, it's in a D block. So it should be last putting electrons into a D subshell. So an electron configuration for tungsten. Now, or like I would probably think of just doing this relative to xenon, the nearest preceding noble gas of xenon. But if you're not sure what that means or why I would necessarily go to xenon and pick up from xenon, then let's think of what the xenon configuration is for a minute. So the configuration of xenon, and the easiest way to get this is just following the periodic table. We just go 1s2, so there's 2 elements across the s block. We can get 2 into the next s. We can get 6 into the 2p subshell. We can get into the 3s subshell, we can get 2. So we're just kind of looking at the periodic table that you're almost just going from S to P, back to S, back to P. So the next subshell is a 3p6, just follow the periodic table. Then we get to a 4s2. Then we go across the D block for a 3d10. Then we go across a 4p subshell for 6. That gets us through krypton. And so then rubidium, strontium, that would be the 5s2. And then we got to go to the next D block, so that's going to be a 4d10. And then across the next P subshell. And so again, boron's a 2p, aluminum's a 3p, gallium's a 3p, so indium's going to be, boron's a 2p, aluminum's a 3p, gallium's a 4p, indium's, and across would be the 5p. So this is going to go back to a 5p6. Just making sure that we understand where all these numbers are kind of fitting into each other. And so that's the xenon configuration there. And so picking up from xenon, we'd go cesium, barium on a cross, so that's going to be the next S block. So the next S block would be 6s2. Then we got to go across, just follow the elements. We got to go all the way across the F block, 4f14. Our periodic table is kind of silly. Like, periodic tables kind of vary in what element they put in that first D block. See how our element 57 is shown in the D block? That's kind of weird. Most periodic tables, and the one you get on your test, puts it down below in the lanthanide series. It is the element lanthanum, so it is starting the lanthanide series. And so every periodic table just has an issue of, like, how do we show you the wedge out? Most periodic tables would either just leave that blank, and then the last element, lutetium, would be in the spot in the periodic table. So this will probably... Okay, yeah, so anytime I leave the app, it stops recording, so I'm starting to record again. So we go across 14 elements across. Now, how do you know it's 14? Well, you can either count 14 across. If you're using the periodic table in the test, you actually have 15. So you'd have the 14 F block, then you'd have the first D block shown down there. But we're going to come back to the D subshell next. We already filled across the 4D previously, so we come to the 5D. And so then you can count across. So, like, the way I would probably count is just to start from how many across tungsten is. See how chromium's 4 across, molybdenum's 4 across, tungsten's 4 across. So it's going to be a 5D4. So it's possible you might miscount this as 3, like you may be like confused in terms of, like, where do we count the 5D1? Well, technically the 5D1 is element 71. But one trick or one double check is just to always count the electrons. If you double check your electron count, it's pretty hard to make a mistake. So we have 54 for xenon. How do I know that? It's element 54. So we should have 54 here. I'm not going to take the time to count, but assuming I didn't write anything wrong, that should be 54 electrons. And so we have 54 for xenon, plus 2, plus 14. So that would take us to 70. And then plus 4 should take us to 74 total electrons. And we should have 74 total assigned for tungsten. So tungsten 74 should have 74 electrons. So if you get a big element on the test, like this, just do a quick double check. Just count the electrons that you assigned, compare it to the number you should get based on the periodic table placement of the element. So that gives us a 5D4. In terms of valence count, if we're counting valence electrons, this is like a weird count here because the outermost shell should count for sure. So we have those 2 for our valence electrons. And then these 4 here should count too because that's a lower but unfilled subshell. So we should get 6 valence electrons. Just like if we had chromium, we would have said 6 as well for chromium. So following along with an unfilled subshell counting in towards the valence gives us 6 valence electrons. Now our valence diagram, we would tend to think of just showing the valence orbitals here. I could write out all the 4Fs. Not much of, like, we just spin pair 7 orbitals with 2 electrons each. So I don't know if we really want to take the time to always show like 1, 2, 3, 4, 5, 6, 7 orbitals for the 4F. And it's also not part of the valence. So when I'm thinking of a valence diagram, if it's not really a valence orbital, I probably don't think of including all of these, but I could. So we try to go 7, spin paired, 8, 9, 10, 11, 12, 13, 14. And then 6s2, and then 5d4. So the key is just pairing the electrons in the same direction. That's Hund's rule. So we try to use Hund's rule, maximize the spin when filling into orbitals that are of the same energy. And then we can get a maximum of 5 spin paired electrons into a d subshell, then we have to start spin pairing after that. So we have 4 unpaired electrons, and we have 6 valence electrons. Now, sometimes you wonder why we ask the questions on valence count. Sometimes the valence count is just because those are going to be the elements, or excuse me, the electrons that are important for bonding. As we get into chapter 8 next time, it's going to be really useful for us to know that these are going to be the elements that are participating in bonding. We're going to be counting these up when we start Lewis structures in the next chapter. So coming up with the right count for valence electrons is really important as we get into chapter 8 later. And then the unpaired count, this is just kind of like a way that we can ask a question that makes sure we have the right configuration, and then we have the right way of putting the electrons into the configuration. So if you were to say like 0 unpaired electrons, you either have the wrong configuration or you misapplied Hund's rule applying electrons into the subshell. If we did something like this, if I took this subshell and changed it like this and put 2 electrons spin up in one of the orbitals, why is that wrong? that's a Pauli exclusion principle violation. So that would show an orbital or two electrons that share the same set of quantum numbers. So that's a Pauli exclusion violation. You would probably say it violates Hund's rule too, I guess. But so we want to maximize the use of orbitals. What we're doing is we're spreading electrons out by putting them in the different orbitals. So that helps the electrons that repel each other from minimizing their repulsions. So the next question just asked lead. I think we did lead in class, so I don't know if, is there an element you guys want me to change this to? Because we did lead in lecture previously. Any element anyone cares about to throw out? Sure.
Do one of the elements that has an amount on the list?
Yeah, well, I mean, like, if we do, like gold, for example, or what were you going to suggest?
Materium.
What's that?
MT.
Good job knowing the element. So meitnerium, element 109 was thrown out. Let's go through lead and go through that one too. So for something like gold, I would just say, just be able to tell us the expected configuration, because the anomalies, I don't want you guys to memorize the anomalies, because there's only one group of elements that all share an anomaly, and it's only for 3 of the 4. So it's only copper, silver, and gold all do the exact same thing periodically, and then Roentgenium or Roentgenium, whatever you call it, one. RG doesn't do the same trend or do the same configuration anomaly, but it's probably because that element exists for like 2 seconds before it decays into something else. They probably just can't characterize it, would be my guess. But for gold, its configuration, I would say know the expected configuration would follow along from xenon, 6s2, 4f14, and then it's across the 5d for 9. And then it does have the anomaly, but I wouldn't expect you to memorize this, but it does have the anomalous configuration of xenon 6s1, 4f14, and then 5d10. So if I tell you an element has this configuration, and I say, okay, there's some element has this configuration, what is the element? The simplest thing that you do is you just count the electrons. You just take the 54 plus the 1 plus the 14 plus 10, and that should take you to a total of 79. So that should be element 79, which would match gold. So if you're given a configuration and you're told it's anomalous or it's not the expected configuration, then just count the electrons up. Very simple to determine the configuration if given, determine the element given a configuration, because you're just counting electrons at that point. If we ask you for the configuration, we're always going to be generally looking for the expected. I mean, maybe we could say gold has an anomalous configuration. What is its configuration? But to me, those questions are kind of like, maybe for gold, silver, copper, they're pretty easy. For palladium, it's easy, but platinum's weird. If you look at platinum's configuration, it ends up being a 6s1, 5d9 for some reason. It makes no sense why it would do that. And then like ruthenium and rhodium do something strange too. So I mean, there's a lot of configurations that don't make a lot of sense. The F block gets strange too. They can move electrons around, but it's only for like a small handful of those. So just know that there are some of these anomalous configurations. Let's do the valence diagram for the anomalous configuration. So our valence diagram, I guess, would just be this one here, because we now have filled the d subshell. So I suppose for gold, we might say it only has one valence electron. It'd be a trick question. It'd be a tough question to answer if we asked you for the valence count of gold. If you look at this configuration, you'd probably say it has 11 valence electrons. If you look at this configuration, you might say, well, it's filled, the d subshell only has 1. So not a great question for gold in terms of its valence count. But if we use the anomalous configuration, we would just have 1 unpaired electron, and then we'd have maybe just 1 valence electron. So 1 valence, and that 1 is unpaired. Let's look at the meitnerium, element number 109. So this one here would just follow after radon's configuration. So we're just now down in the 7th row. So I don't know if we've ever done a 7th row element, but we just follow from radon, and then from cesium barium we're 6s2. So now francium radium we're 7s2. Then we go across the actinide series. So we fill across the 5f with 14, because we can only get 14 electrons into the 5f subshell. Then we get the lawrencium on the end, and that kind of starts us back into the now 6d subshell. So the last d block elements, we went from 3d for scandium, yttrium for the 4d, lanthanum for the 5d, and across the actinium series into that d row, that would be into the 6d. So we go 6d across, and we're just counting 1, 2, 3, 4, 5, 6, 7. Should be a 6d7. And again, we could double check the electron count. So radon's 86. Over here, it's closer. 86 plus 2 plus 14 plus 7. Sounds like 109 to me. Okay, so that's, configurations aren't entirely tricky. The only tricky part is just, I think, knowing how to apply the periodic table and just kind of starting with the 1s and the 2s and the 3s, 4s on downward, starting with the 2p on downward, starting with the 3d on downward, and then the lanthanide series, it's a 4f. So sometimes a question may just like kind of pose, is this going to be a 7f, a 6s, or a 5f? And it's just a 5f. Okay, let's get into some chapter C. Add a slide and think real quick. Let's go through our trends real quick in terms of how they change from left to right and from top to bottom. So the left to right trend for effective nuclear charge is that this increases. This is what gives us the big change in trend or properties of elements as we go from left to right. This is the main explainer on why we're going from easy electrons to lose on the left side, making cations, to then harder electrons to lose on the right side, and then doing the opposite, forming anions instead of cations. And so we get this big increase from left to right, then it resets itself with each successive row of the periodic table. And so this is where we're getting our periodic behavior. So periodic behavior comes from the effective nuclear charge trend. And the idea here is that only those core electrons effectively screen each other from nuclear charge. So as you go from left to right, you have a constant core, at least for the first three rows of the elements, first three rows of the periodic table, you have a constant core. So for hydrogen, helium, no core, so that's easy. Lithium, beryllium, and across a neon, you have 2 core electrons from left to right, and then you have 10 core electrons for the third row. So the core is constant. As you go from left to right, the nuclear charge increases, so more of that charge makes its way out, and that serves to increase the effective charge. Let's think of the other left to right trends real quick. So let's think of the atomic size of the radius. So just remember, atomic radii is how we think of size. So size decreases left to right due to that increase in charge. The increase in charge pulls the electrons in. So as we go from left to right across a row, elements are decreasing in size. And then if you think of the ionization energy, that this is increasing for the same reasons that you have an increase in the charge, and then a decrease in the size. And so both of those factors would lead the ionization energy to increase. And we just have a periodic inconsistency with the NP1 and the NP4 groups. So the boron group and the oxygen group are just a little bit lower than we would have expected. But generally speaking, we do have the decrease in size, the increase in effective charge. These periodic inconsistencies are coming from what I call orbital anomalies. These are coming from the fact that we're removing electrons from lithium, beryllium from an s orbital, and then boron first from a p orbital. P orbital is just bigger. So we're just not really comparing apples to apples when we look at ionization energy trends from left to right so that we get these anomalies. But we do have a decrease in size and an increase in effective charge. These two trends here are always decreasing for size, always increasing for the effective charge without that anomaly. So this is just due to configuration. So just a configuration issue with that trend leads there to be that anomaly. I wouldn't worry too much about the anomaly. This is just the one that led to the increase, slight decrease, back to an increase, and then a little bit of a decrease, then back to an increase. So this is just explaining or noting that there is this inconsistency with ionization energy. And then electron affinity becomes more negative. More negative is smaller towards the halogens. And then if, the most positive group, though, the highest group would be the noble gases. So we decrease, go more negative towards the halogens, and we reset with the noble gases. So electron affinity would be an atom absorbing an electron to go to an atom minus. Most elements in the periodic table have negative electron affinities, meaning that the electron is absorbed and energy is given off, so the electron is accepted in and lowers the energy of the atom. That's a good thing for the atom. It wants to do that when it lowers its energy. Losing an electron for all the elements is always positive. So every ionization energy, so an ionization energy is where an atom loses an electron. that ionization energies for elements are always positive. So it always takes energy to remove an electron from a neutral atom, and then it requires even more energy to take the second electron away, even more energy to take the third electron away, and a dramatic increase in energy whenever you remove a core electron. So removing a core electron takes a lot more energy. So think about magnesium loses an electron. It takes however much energy that is. If you remember, I think it was like 700 or 1,000-ish kJs per mole. The next electron took about double that value, so the second electron takes a little more because that last electron is a little bit closer to the nucleus. Taking electrons away decreases the size of the ion, so magnesium plus takes a little bit more energy to remove its electron, and then for magnesium 2 plus to lose an electron, think about the core. You're now removing a core electron. It takes a lot more energy to remove a core electron, so big increase for removing core electrons. Okay, so now let's think through the top to bottom trends. So the effective charge, you get a slight increase from top to bottom. This trend is a little bit tricky to understand. The two ways I like to think of it are either A, as you imagine a bigger element like cesium. So cesium has a core that's pretty big. So cesium's core electrons are pretty big, allowing cesium's outer valence electron to have a relatively high probability for being near the nucleus and experiencing a greater or relatively greater effective charge than you would imagine it should have if the core were smaller. So when the core electrons are smaller, they kind of block the nucleus, they block the region closer to the nucleus from those outer valence electrons. So as the core electrons are growing bigger, they're allowing those valence shell orbitals to get a little bit closer to the nucleus on average. But then the second way you can think of this is just through like these probability diagram type spectrum, so that as you imagine an orbital in something like a 1, 2, 3, 4, so 4 nodes. So these are representing nodes, of which there's 4. So this would be representing a 5s orbital. So remember how a 1s has no nodes, a 2s has 1, a 3s has 2. So a 3s would have 3. So this would be showing us like something like a 5s orbital. And so all these probabilities added together are why that 5s electron is having an increased effective nuclear charge, because those are kind of showing that the larger core electrons are allowing that bigger 5s electron to experience some probability for its electron being relatively close to the nucleus. So this is like a schematic picture of how that happens, but you get a slight increase from top to bottom. You get an increase in size, big increase in size as you go from top to bottom because we're using bigger shell orbitals. So packing more valence electrons from top to bottom increases size. But from left to right, adding electrons didn't increase size. As we go from sodium to chlorine, chlorine's smaller than sodium as you go from left to right because we're increasing the effective charge. From sodium to potassium to rubidium, we're just using larger successive shells, so size increases. Now, ionization energy trends, how does ionization energy compare? Well, generally you get a decrease in ionization energy. Now these two trends here counteroppose each other. If you think of the energy of electrostatic attraction, kappa Q1, Q2, divided by D, the size trend is the outer valence electrons are further away, they're less attracted. The charge does go up a little bit. So do you see how the effective charge going up? So if you go from like sodium to potassium to rubidium to cesium, the charge is going up a little bit, but the size is growing up presumably by more. So the size trend is winning. So the size trend wins out. So due to the increase in size, despite the small increase in effective charge, ionization energy trends tend to decrease from top to bottom. For a handful of elements, we pointed out that there is an increase. So at least for a handful of elements, you can see for those, the effective charge must have been a larger increase for those compared to their size. So it's just all about, was the charge increase greater or was the size increase greater? Just know that the effective charge increase from top to bottom is a small increase, not a very large increase. And then the effective nuclear charge trend, there's effectively no trend. I mean, there is a trend, but there's not much to speak of. There's not much I really want you guys to focus on. Like we pointed out how the third row, like the chlorine row, just happened to balance for electron affinity, the right balance between size and charge. If you think about the halogen group, which one's the most, of F, Cl, Br, and I, the 4 halogens actually exist naturally. Which of those 4 elements has the highest effective charge? Fluorine or chlorine? Or fluorine or iodine? Iodine does, because effective charge increases from top to bottom, but iodine's bigger. So you can see an electron going in, you can say, well, the charge goes up, that's good, but the size goes up, that's bad. So fluorine, it's like really small, has a relatively high effective charge, but not the highest. So it turns out chlorine was the most negative. Not that I would memorize that, but chlorine just had the right balance of its effective charge was a little bit higher, and its size when you add the electron was the right size. Its electron was the most favorable to be absorbed in from top to bottom. So the third row is pretty much the best row, but I wouldn't necessarily take too much away from that other than there's not much of a top to bottom trend in terms of the electron affinities. Review topics. So effective nuclear charge, so let's maybe think about how our, in fact, okay, so which atom has the greatest effective nuclear charge? So a lot of these are just kind of like rearranging or making sure we're kind of comparing these on the right groups as each other on the periodic table. So the greatest effective nuclear charge, because we're increasing this way and increasing this way, would be iodine. The lowest would be lithium. Which atom below has the largest atomic radius? So radius, if we think of left to right, it's increasing to the left and it's increasing to the bottom. So largest radius, these are all uncharged too. So whenever I'm asked about size, I might want to do a quick inspection to see, are they talking neutral atoms or are they talking ions? We're talking neutral atoms here, so I'm using my atomic radii trends. And so whatever is to the down and left is going to be the biggest. So if I remake a little periodic table, so it's going to be sodium. Sodium's bigger than lithium. Lithium's bigger than nitrogen. Sodium is smaller, or excuse me, sodium is bigger. Sulfur is smaller than sodium. Size decreases left to right, so sulfur is going to be smaller than sodium, so sodium has to be the largest. So now we're comparing ion size. We have to remember cations go smaller. I think that makes a ton of sense, right? You take an electron away from sodium, it just has its core. So sodium plus has to be smaller. So cations are always smaller than their neutral atoms. Anions are always larger than their neutral atom. Because if you add an electron onto an atom, that electron, all the other electrons repel it, causing the size of the atom or the ion to increase. So sodium plus, we're looking for the one that's greater in size. So sodium plus is smaller, so sodium has to be bigger. F versus F minus, adding an electron into fluorine makes the anion grow larger than its neutral counterpart. Here I have to compare the atomic radii trends. So here I use my trends for my left to right trends that we were just talking about. So I might also make a comparison with lithium. That sodium is bigger than lithium. Lithium is bigger than fluorine, so sodium has to be bigger than fluorine. So sodium's bigger than fluorine. And then that's probably going to flip here. So, because again, sodium plus is smaller, fluoride is bigger. What I have to compare here are the positive particles. Each of these have 10 electrons. Sodium plus, sodium has 11, take an electron away has 10. Fluorine has 9, add an electron to fluoride, it has 10. So they each have 10 electrons. That's isoelectronic. I don't know why I spell things. Isoelectronic, meaning they have the same electronic configuration. So if you're an ion, you have a 1s2, 2s2, 2p6 configuration. Are you pulling those electrons in more closely with 9 plus or 11 plus? 11 plus. So having more protons is better. So here we're counting the positive protons. So if I have an 11 plus charge to hold in the same configuration, that's going to make the ion be smaller than if we had 9 plus. And so that makes sodium plus smaller, makes fluoride bigger. And so sometimes this is confusing. I don't think it's confusing, but it could be confusing if you don't understand how for ions we're comparing their proton count when they have the exact same electron configuration. If we're comparing ions that have the same charge, i.e. they're all uncharged, we're using the left to right trend. We're using the simple trends of size from left to right on the periodic table. So whatever answer that works out to here is answer A. Question 4. What is the general trend and proper explanation for the first ionization energy of an element from top to bottom? of a column of the periodic table, i.e. decreases because atomic size decreases. Atomic size doesn't decrease from top to bottom, so that can't be right. Ionization increases from top to bottom because the effective nuclear charge increases. The effective nuclear charge does increase, but that's not the explanation, right? Because the effective nuclear charge increasing would have made us think the ionization energy should, well, the ionization energy doesn't increase, the ionization energy decreases. So statement B is wrong because the IE doesn't increase generally from top to bottom, it decreases generally from top to bottom. The IE1 increases from top to bottom because the effective nuclear charge decreases. That doesn't make any sense. The effective nuclear charge doesn't decrease from top to bottom, it slightly increases. But then the I1 decreases. The first ionization energy decreases from top to bottom because atomic size increases. That's the proper explanation. And you can even then add despite the effective nuclear charge increasing with the same trend. So despite the fact that effective nuclear charge increases, the ionization energy decreases due to the general increase of atomic size from top to bottom. I don't know, like if another question, a question we'll probably get into, but I wanted to make sure we can write first versus second versus third ionization. So if I don't see a question on that topic, I want to make sure to talk about that. So which statement here is correct about ionization energy? The first ionization energy always increases left to right. That doesn't sound right because we have that periodic inconsistency. And so that doesn't sound like a correct statement. Electrons closer to the nucleus have a lower ionization energy than electrons residing in larger orbitals. That sounds pretty good, so that sounds like it could be the right answer. The 2s electrons in oxygen have the lowest ionization energy of all of its electrons. So if you think of oxygen, it has a 1s2, 2s2, 2p4 configuration. Those 2p4 electrons have a higher energy. If we're thinking of the electrons going in, they're going in this order here, so the electrons are higher, they're closer towards ionization. So if you remember from the Bohr model, we had the Bohr model, n equals 1, n equals 2, n equals 3, n equals 4, and eventually we had n equals infinity, and that was ionization. So you can imagine that at some point the electrons can be removed from the atom. The higher an atom starts, the higher the energy level of the orbital with the electrons, the closer it is to ionization, the easier it is going to be to ionize those electrons. So the 2p electrons, easier to ionize, they are removed with a lower energy than the 2s electrons. The 1s electrons require the greatest energy to be removed because they're the closest to the nucleus. So it should just go the order of 2s to 2s to 2p. Thinking of how big these electrons are, so 1s to 2s and then the 2p are larger than the 2s electrons. So C sounds incorrect. D, compared to the first ionization energy, the second ionization always requires greater energy. That is certainly true. So I'm thinking D's the right answer. I need to come back to B on why I thought it was right. So we'll come back to B in a minute, but let's look at E. So energy is released by an atom when it loses an electron. Now, why, sometimes you might think that's right because we so often see sodium plus, K plus, and Rb plus. You might think that they had formed because it was exothermic to form them, but it's not. It's endothermic to form them because energy had to be absorbed to break the attraction that the electron had to its nucleus. All ionization energies are positive, so those ionizations are endothermic. Now, why then does potassium not exist naturally in its solid form as K solid? Why does it exist, like if you find it in Earth, it's always going to be in its cation form, never in its elemental form? And the reason why has to do with once you ionize the electron, make K plus, and once you take the electron from it and put it onto something like chloride, and you have the chloride minus ion, you get the electrostatic attraction. So we haven't yet tried to factor in that it's that electrostatic attraction that drives the formation of the compounds to be ionic in nature. Okay, so so I think I misread B. So it says electrons closer to the nucleus have a lower ionization energy than electrons residing in a larger orbital. The closer to the nucleus would make the ionization energy be higher. So being closer to the nucleus, I just misread that. So this should result in a higher ionization. So harder to remove the electrons that are right on top of the nucleus because they have that much more strong attraction to the nucleus. So answer D here would be the only correct answer. Question 6, consider the following pairings ranked on size. So aluminum, silicon, phosphorus. That would appear to be wrong because phosphorus, these are all left to right elements, so phosphorus should be smaller than silicon, smaller than aluminum. Beryllium less than magnesium, less than calcium than strontium. That is true because that's down the beryllium group. So as you go from top to bottom, size increases. So that looks correct. Iodine less than bromine, that's incorrect. Fluorine's the smallest. I assume this was size. I should probably read the question correctly, right, or fully. So consider these trends. Let me read the question. It says, which of the above gives the correct trend for increasing ionization energy for one electron from the atom or indicated ion? Okay, so let's start over. So this is looking for ionization energy trends, not size. So ionization energy, aluminum to silicon to phosphorus, those would increase, so that is correct for ionization energy as you go from left to right. And aluminum to silicon to phosphorus, if we're even thinking of that periodic inconsistency, that's not part of the inconsistency, so that trend should increase. Beryllium, less than magnesium, ionization energy should decrease from top to bottom, so I1 should decrease from top to bottom, so that trend would look to be incorrect. If ionization energy decreases from top to bottom, then iodine would be lower than bromine, lower than chlorine. So this would be the general trend for ionization energy for trend 3. And then what about the removal of an electron from sodium plus, magnesium plus, aluminum 3 plus, silicon 4 plus? So these all are isoelectronic. So this is just like size. Remember, from size, we compare the number of protons. And so we'd say that silicon 4 plus is smaller than aluminum 3 plus, magnesium 2 plus would be a little bit bigger, sodium plus would be the biggest because the more protons that hold the same number of electrons in. So now if you're removing an electron, which electron is going to be harder to remove? The one with 10 electrons but where you have the 14 plus charge, or the one where you have 10 electrons but an 11 plus charge? It's going to be a lot harder to remove the electron off of silicon, so I think this trend here is perfect. That the trend for 4 is exactly as you would expect, that the ionization energy trend will follow the general size trend and also that isoelectronic series trend. So just applying what it would mean for silicon 4 plus to be smaller should lead it to have, therefore, the greater ionization energy. So 1, 3, and 4 would look to be the correct answers here for this one. What is the electron configuration of gallium 3 plus? So gallium 3 plus just right next to zinc. So gallium 3 plus. Think of the configuration of gallium neutral. So gallium neutral would be an argon, the nearest preceding noble gas. Then 4s2 across that first D subshell, so 3d10, then a 4p1. The valence electrons would be these 3 for gallium neutral. And so then we're going to first lose the electrons from the highest N with the highest L. The highest N with the highest L is the 4p, so just lose that one electron. And then the next highest N with the next highest L would be the 4s electrons. So the configuration here should be an argon 3d10. And the key is that this isn't like an anomaly. This isn't weird. This is the rule. So the rule for cations, when you're losing electrons from a neutral atom, take the electrons away from the largest orbital first. So you're taking the electrons away from the largest orbital first. Because they're the ones that experience the lowest overall ionization energy. So if the electrons closer to the nucleus are held onto more strongly, harder to remove. Electrons further away, easier to remove. So the 4p are the biggest for gallium, lost first. Then the 4s, they're lost next. The 3d are a lot closer to the nucleus, they're not lost next. So we don't lose the electrons in the same order we filled them into the configuration. We don't lose them from 4p, then the 3d. We lose them from the 4p and then the 4s. You also can think you're losing the valence electrons. So hopefully we get to answers like argon 3d10 for this question. Question 8, another size trend. So which trend is correct from largest to smallest? So again, this is just ranking based on number of protons. We have 12 versus 11 versus 9 for fluoride. So fluoride would be the biggest, sodium would be in the middle, magnesium having the most protons would make it the smallest. So size trend A looks to be correct. And then the others, like fluoride, is not the smallest anymore. It's the smallest if you compare without the charge. If we're just comparing fluorine, fluorine's going to be smaller than magnesium. Sodium's the smallest, or the largest from left to right. Sodium's larger than magnesium. So we have this basic trend for, if these are all neutral, but once you start adding and removing electrons, you're just changing the size of the cations to be smaller, fluorine becomes bigger, hence you reverse the trend. So just use the isoelectronic series, count the number of protons, fewer protons, bigger size. Question 9, which atom contains 2 unpaired electrons in its ground state configuration? So nickel 2+, lead 2+, zinc 2+. This is just requiring us to correctly identify the electron configurations. So let's look at nickel 0 first. So nickel neutral is a argon 4s2 3d8. Now this really is its configuration. You might think, does it jump to like a 3d10 configuration? It doesn't. But even if it did, I think you're going to still get the right answer here, because we're going to lose the 4s2 electrons first, lose the largest electrons first, the greatest n value electrons of the atom with the highest L value if there's more than one n value sharing that highest n. So we lose the 4s2 electrons here and go to argon 3d8. So in a 3d8 configuration, how many unpaired electrons does that have? Has 2. So having 8d electrons leads us to have a net number of 2 unpaired electrons for the atom. All the electrons are spin paired for argon. So we have 1s2, so that's spin paired, 2s2 spin paired, 2p6 spin paired, 3s2 are spin paired, 2p6. So it's always going to be these electrons out here that would have any unpaired electrons. These are all spin paired here. So 2 unpaired for nickel. Let's look at zinc next. So for zinc is neutral is 4s2 3d10. And so the key is you lose the s electrons first. So you lose the largest electrons first. So we come up with a 3d10 for no unpaired electrons. So 0 unpaired for zinc, 2 unpaired for nickel. And lead is in the carbon group. Like it has the xenon 6s2. So lead neutral would be xenon 6s2, 4f14, 5d10, and then 6p2. So we lose the 6p2 electrons. And then these are all spin paired. So we have 0 unpaired electrons for lead 2+ as well. You may or may not have, if you're really good with the diagrams, you could have been like, well, it's a p2, it loses the 2, and everything else is spin paired. So all these are spin paired electrons. So that's the only valence electron left. These are, of course, all spin paired. So the only one here with 2 unpaired electrons is nickel 2+. Question 10, which atom below, another size question, too many size questions on this, but lithium versus fluorine is left to right size. So we're looking for the smaller, fluorine smaller, oxygen smaller than its anion. Adding electrons makes the anion grow bigger, so the neutral atom is smaller. And then 17+, scandium 3+, these both have 18 electrons. So 18 electrons with 21 protons. So we have 21 protons for 17, 21's better. So scandium 3+ is smaller. So scandium 3+, F and O. And then the one thing I wanted to mention was just the writing reaction. So if you're asked to write like an electron affinity reaction, you know, say for fluorine. So that would be fluorine plus an electron going to F minus. So you just have the neutral atom plus an electron going to F minus. Sometimes we call this the first electron affinity. So like if you wanted to write, say, the second electron affinity for O, so O's first would be this. O plus an electron going to O minus. This is the first, so that's the EA1. And the EA2 would be O minus, absorbing the second electron to go to O2 minus. And this is the same business if you were to say write the first IE versus the second IE. So let's do the IE1 of oxygen. So IE1 of oxygen is oxygen losing an electron to go to O plus an electron. The I2 is the energy associated with O losing from O plus, that second electron to go to O2 plus an electron. So the second ionization is always the energy just for the loss of that second electron, not for the loss of both electrons combined, but just the loss of the second electron. The third is the O2 plus to 3 plus. So the next one would be the O2 plus to O3 plus an electron. So that's the IE3. I think like the only last thing I want to mention before we depart here is just that you can think of the effective nuclear charge of more than just the outer valence electron. So if you're thinking of like sodium, you could be thinking 1s2, 2s2, 2p6, 3s1. And we did this in class the other day, that the effective charge would just go, the 1s experiences the greatest charge, then the 2s, then the 2p, then the 3s. This is just kind of going with the size of the orbital. That you can compare the effective charges of other subshells other than just the outer valence electrons. And you can sort of compare that for like sodium, its 1s would be greater than its 2s effective nuclear charge, greater than its 2p, greater than its 3s. We were using this for like zinc to reason out that its 4s had experienced a lower charge than the 3d. So being further away gives the atom gives that subshell a lower overall effective charge than its other subshells that are closer to the nucleus. All right, so that's all of our time for exam review. Good luck on the test tomorrow, and we'll meet back here and move on to Chapter 8 on Wednesday. See you guys.